I'm pleased now to introduce our second keynote speaker, Dr. Michael Idelchik. Michael is Vice President of Advanced Technologies for GE Global Research, which is the centralized R&D organization of GE. In this role, he oversees the company's longest-range technology endeavors and innovation processes. He started with GE in 1978, progressing through various engineering and management roles within the aircraft engines, healthcare, and lighting divisions, a diversity of experience. In 2002, Michael founded GE's first integrated technology center in China and served as its managing director. He has received many distinguished awards and honors during his career, including the Chairman's Award for Technology Leadership, which recognizes a lifetime of achievement in innovation. GE has been a global leader and early adopter of the approaches that we've just heard about that form the foundation of the Materials Genome Initiative. My own first contact with GE R&D on ICME took place over 20 years ago at the University of Michigan. So I feel that Michael is uniquely qualified to lead off our discussions about industrial adoption of these practices. His presentation today draws on this history of innovation at GE and is entitled Reinventing Industrial R&D. Michael.
Okay, thank you. It's my honor and privilege to be here today. And what I'd like to do in the next 25 minutes or so is to share with you GE industrial research experience, why we had to start thinking very differently about it, how it can be extended, hopefully, to other industries, and how it can play a key role in US competitiveness. Let me start with a couple of slides on GE in general. Under Jeff emailed our chairman and CEO leadership, our investment in R&D increased 3+ times rate of inflation, so to speak. And today it represents over approximately 5+% of our industrial revenue. So Jeff really was a great supporter of technology from the very first day. I happened to work for Jeff in medical, and he's just a real supporter and visionary where GE and the country need to go. A couple of words about our centralized research. We're one of few companies left with centralized research. It is the oldest US industrial lab. We celebrated our 110-year anniversary a couple of years ago. The founding principles never really changed. It's improving business through technology. And we are, I believe, the world's most diverse industrial research lab, a true cornerstone to commitment to technical innovation. It's a global organization, headquarters in East New York, next to Schenectady, where we have approximately 1,900 people, 65% PhDs. It's distributed. Now we actually have 3 locations in the US. What you see here is a center in Michigan, manufacturing and software center. There is another software center just been announced in East Bay in San Francisco. We have location in Europe, right at the grounds of TUM, Technical University of Munich. China, that's why I spent 2 years of my life building. Bangalore, India, and center in Brazil is coming up pretty nicely, and it will be operational in 2013. Just looking at how GE organized today, our largest business is GE Energy Infrastructure, which combines energy management, oil and gas, and power and water business. Our healthcare business and aviation, each one of them is around $20 billion businesses. Transportation business, home and business solution, which is a combination of businesses from lighting to appliances to intelligent platforms. And our restructured and focused GE Capital, which is a great part of our company. So just kind of quickly go over the environment. You're probably all familiar with that. One of my friends who doing economic strategies called it a slow grind. You know? even in slow grind, what we see is rising cost in materials and constraint in supply chain for some of them. We see overcapacity, and for GE, almost in every industry we are in, there is overcapacity. We see labor cost rising significantly in the developing world. And it's all combined with fiercely competitive marketplace, where customers demand shorter cycle times for development and more price points. So when we looked at that environment starting in 2005, 2004, we decided that we really need to think differently about industrial innovation. And I'm going to give you kind of example. We're going to stay on the chart maybe a little bit for just kind of getting at how we think about it and how we'd like to think about it. In the world of industrial innovation, it was assumed, and rightfully so for a while, that in the design innovation phase, high risk mean high payoff. And design really drives selection of materials and manufacturing processes. On another side, it's also been assumed that low risk translates to higher payoff in material selections and manufacturing processes. So this process is mostly sequential. It's create few interactions between manufacturing and design. In at the end, it limits design options. We also concluded that with this model, competitors can relatively easily follow the new designs and innovations, because there's really not that much in originality in innovation and supply chain. The new model we work into for the last number of years is a combination of design innovation, manufacturing innovation, and materials innovation. It's a non-sequential process. It creates a lot of interactions, and it creates really new degrees of freedom in design. And we believe it creates a longer-term competitive differentiation. I'll give you a couple of examples. In aviation, we introduced first intermetallic in Billet in aircraft engine history of aviation altogether. The original patent for materials came in late 80s. We tested it in an engine. We made a commitment to that technology. And for the next just about 15 years, it took to develop the right processes, right properties, right manufacturing technology to meet production goals of cost and quantity needed. We are extremely excited about this technology. It's called thialuminide. It's created a true competitive differentiation for our new engine, which powers this beautiful 787, our GNX. So here's an example where new material and new manufacturing processes open a whole new design window for our turbine designers. Another example, healthcare. It was clear to us a number of years ago that creating spectral imaging, ability to bucket X-ray different energy during the imaging, will create a really paradigm shift in CT. The gemstone detector was patented, formulation was patented in 2003. It took us a while to get it right, just about 3 years, but we made a product commitment to that technology, just like on an engine side. CT had to come out with this technology being integral part of it. So it starts with gemstone detector, which translates X-ray to visible light, have a photodiode, and very low noise electronics to be able to read really picograms. And that combine it all in a fairly complex computational algorithms to the image. This is a unique technology which made CT a world leader, a world product leader, and first of its kind to be able to really image beating heart, and score calcifications due to its spectral capability. So what we have learned, manufacturing materials can differentiate products, but it's not without risk. There are definite opportunities, drive new product capability, give designers a completely new degrees of freedom, and provide long-term competitive advantage. Challenges are, takes long-term trends identification. You need to really know where you want to go. Willingness to take high risk. Bets really on, you make a bet on unproven technology, on unproven idea, and demands long-term commitment. So when we think how to extend this model to other industries, into more products, even with our own portfolio, we think we need to find a model to allow us to share risk and rewards, of course, share knowledge in innovative ideas. What we're really thinking about is industrial ecosystem. And when we look at industrial ecosystem, we have players, interactions, and outcomes. In the players, of course, industry, government, universities, national labs, and venture capital. Infrastructure, shared infrastructure, equipment, funding, knowledge, risk, award, road mapping, and of course, legal framework to be able to do it all in the right way. An outcome needs to be US competitiveness and jobs. So as we thought more about ecosystem and what it has to deliver, we come up really with two major goals. One is to make a step change in efficiency of innovation. I personally look at over 70 companies a year, startups. And they don't lack great ideas and concepts. What most of them really need help on is to understand how their innovation can fit into complexity of today's supply chain. How do they fit in the whole equation? And another thing they're really missing is what it takes to scale some of those technologies up. So the first priority in our view is ability for innovators and entrepreneurs in small and medium-sized companies to really understand how they fit in the complexity of today's supply chain. And the second one is kind of visibility of new ideas, guidance, and support of how to scale those ideas to actual products. So this is for us number one. Number two is really rebuild talent pipeline. If I want to hire metallurgists today, that's non-trivial exercise. If I want to hire a structural ceramicist, it's non-trivial exercise. So we need to make manufacturing technology in material science cool and exciting for our students and faculty. And we really need to start investing again in applied research. So as we look at timeline, innovation efficiency, we can do today. We can do it now. I think we really can make a step change in it. And the talent pipeline needs to be built. We're really starting from ground zero in many universities. Then we compare two models, two R&D ecosystem models. One is National Nano Initiative, NNI, and another one is Sematech. Hopefully you guys are familiar with both. Both successful programs. Both have very well-articulated goals. Approach was different, fundamentally. One was to create a basic research in government universities and translate it to industry. Another one was very clear, to figure out how to protect US semiconductor manufacturing from increasing competition from Japan and Korea. And we were losing ground. And outcomes are there as well. So one outcome is we created 8 national research centers. We created a nanotechnology lab in over 75 universities. An outcome of Sematech is really a very competitive US semiconductor manufacturing industry. This consortia now is of government support. Actually, now since '96 of the government support, and it's very, very prosperous and self-sustaining. So when we look at both approaches, I think the guiding principle for us, from where we see it, in our understanding of the global environment and competitiveness, the guiding principle is speed. Speed for competitiveness of jobs. So both initiatives, just looking at the lessons learned, establish national priority, commit and focus resources, create structured partnership. And then we really looked at US manufacturing and how they can benefit. So when we look at this and score them, yeah, we have a national priority. There's no question about it. I just came back from Asia, actually on Tuesday night. Been in India and China. And I can tell you something, there's nobody waiting for us. No one. So we need to commit and focus resources. And looking at that today, there is no new money, as previous speaker pointed out. It's really a reallocation. Another concern to us is, as we look at structured partnership, the industrial participation is very small today. And I know that AMP is still evolving, but today it's not promising, doesn't look promising. So we honestly prefer a Sematech approach, and we feel that the industry needs to lead. When we look at manufacturing R&D, and it's very closely tied to materials, those three examples I think are good ones. I'm sure you can come up with more. Composite manufacturing, roll-to-roll processing, and additive manufacturing. Each of these technologies is relatively in the early stage of its development, and I think are very, very ripe for innovation and ecosystem around them. How do we move manufacturing R&D ecosystem forward? Again, our view is it needs to be led by industry, enabled by government, supported by universities and national labs. We need to form consortia with the entire supply chain. Shared infrastructure, focus on specific manufacturing technology, and materials, namely ICME, computational capability, need to be an integral part of this ecosystem. And again, ecosystem, in my view, need to accelerate and deliver US competitiveness in jobs. So we are very excited about additive manufacturing. We think it creates a paradigm change. And I think there is nothing on this page which is new to this audience. But I think just looking at conventional versus additive gives you a real perspective of why it can change the paradigm. First of all, you can build material properties as you build a part. And we're doing it today. So you can have properties which are location-specific. You can have shapes which are really non-executable today and avoid a lot of brazing and welding in the process. You can make shapes which are not really realizable, and you can do it faster. You can iterate between design and manufacturing processes. And finally, your tooling costs could be significantly less. In our assessment, ability to design new materials and implement them during the manufacturing process will completely change the paradigm. And we are very much excited about this technology. At Global Research, we support many GE businesses. And when we look at computational material engineering, we clearly can relate it to the work we're doing today, and that's how we're going to actually organize it within GE, in organizing within GE. it relates very closely to our work on cloud-based electronic medical records. We today store pathology slice data, which is terabytes. We store CT, MR, and PET data, which have a terabyte each. We allow radiologists, oncologists, and surgeons to access the data from remote locations. We allow them to debate the data, make conclusions, and store their results. So from GE point of view, that's not undoable. It exists today. We supply our customers with these capabilities today in healthcare world. So finally, what the industry can do? GE will take a lead to establish framework for additive manufacturing. We will assemble industry, university, and government agencies representative at Global Research in Niskayuna. We'd like to really reach an agreement on additive manufacturing ecosystem. We'll do it this year. We started the process already. Again, that's not everything, but I think it's a good start. And I hope that we'll attract representatives from a number of industries, and we already have done it. And we'll attract key representatives from the government, the national labs. So with that, we'll open it for questions and answers. Thank you.